Bismillah ar-Rahman ar-Rahim. Today's lecture is wave properties, which is lecture number 11. We're going to continue on the water hammer for several lectures. I will write آخر semester, inshallah. Wave properties. The two major reference is applied hydraulic transient by Chaudhry, which you already know, and the other reference which is hydraulics of pipeline system by Laroux, Gibson, and Waters. Okay, those are the two reference we're going to use, and only you're going to look for chapter or two chapters from them. Pressure wave properties. Transients move as a pressure wave. We call the wave as a wave speed. We give that as a letter A or C. You'll only look for those two letters in any textbook. A for the wave speed or C. And we're going to use A during our course here. The wave speed depends on several parameters. واحد, fluid properties like density, like bulk modulus, like any other things related to the fluid property. Pipe material, like steel, PVC, the kind of material which is made from. Joints, like flexible joints, for example. Presence of dissolved gas, if it is a lot of gas there or gas bubbles existing there, this is very important. And anchoring, the support, the kind of support. This is more or less the important part or element that affect the wave speed. Assumption. So before you start, we have several assumptions there. Number one, we are talking about. Can we keep the question at the end, Abdurrahman? I will give, like, after the lectures, I'll give few minutes to anybody has any question. Assumption for water without presence of free air, undissolved gases in the form of bubbles. Any water with bubbles, this equation will not be valid, or it will be affected much. Pipe had a thin internal water diameter. The expression of thin is D over E. D is the diameter, E is the thickness. If you divide both of them over each other, so D over E, if it is greater than 40, we call this a thin pipe. And this is definition by Waters, 1984. If you look to the other book or other reference by Strater and Wiley, for example, he said that D over E greater than 25. We are going to use D over E greater than 40 during our course here. Pipe remains full of water, means if it is partially full or if it is not completely full, it will not. This is another topic. This is not the equation which we are calculating right now. So pipe remains full for water during the transient event. No separation. I mean, if there is a column separation there, so the wave speed will not be properly calculated. If there is a vapor pressure, so all the pressure has to be greater than the vapor pressure. This is the third assumption. Number four, as we all know that water has small air content. It dissolved one. So this is not the one which we mentioned at the first step here. Here it's a bubble, clearly bubbles, and this will affect dramatically the wave speed. Here we all know that water has some dissolved air. If it is, the wave speed may be assumed constant at that very small percentage. The pressure is uniform across any section of the pipe. This inertial force associated with radial motion of the fluid are negligible. This is a very high level of research by Sakalik. The guy is 1955, his dissertation. He make an extended theory for the water hammer. Let's concentrate on how propagation of speed. I have a previous question of this section here. This section is not the place of the hammer. The hammer initiated, for example, at a valve closure in the downstream, for example. If the wave moves and reach that section here, this is what we call the section under investigation. In this part here, in the previous lecture, we have A square root of K bulk modulus over the density. This is we call the rigid wave speed, or the wave speed, water sonic speed. And today we're going to take the general expression for the wave speed, which is A square root of K bulk modulus divided by density divided 1 plus K bulk modulus, D the diameter, E is a Young modulus, and the small e is the thickness of the wall. Okay. Now we have to define some parameters here. The first table to your right here is defining the Young modulus of different pipe material. If I have a steel pipe, or a copper, or a bronze, or asbestos, fiberglass, PVC, polyethylene, we have E, a Young modulus, units Pascal. You will find steel 2.07, 10 to the power 11 Pascal. We normally use gigapascal. The gigapascal here at that, if we are trying to say this in a gigapascal, it will be 207.7 gigapascal, i.e. 10 to the minus 9. So here, if we go down, you will find this 2.8 gigapascal for PVC. If you look to the polyethylene, it will be 0.8 gigapascal. Remember, the gigapascal is 10 to the 9th. So this is, you will find this in LaRocque, the second reference, 2000. And if you see to the left of your slide here, at atmospheric pressure 20 degree, at a temperature 20 degrees centigrade, and atmospheric pressure 1 bar, the bulk modulus of water is 2.07 gigapascal. So this is like a standard for the bulk modulus, and we normally use that number. We don't have a table giving us for different kind of temperature, different kind of pressure, what will be the bulk modulus, but let's use this for the sake of understanding how to calculate the wave speed. Let's use that number for the bulk modulus for water as 2.07 gigapascal. Again, 2.07 multiplying by 10 to the power 9 Pascal. At atmospheric pressure, we normally use density as 1,000 kilogram per meter cube. Again, this is the number we're going to use during our course here. So somebody will ask, if I have different temperature, if I have different pressure, if I have different, you have to go to the table and write table and get the exact density of the water and put it in your calculation. Okay. The last parameter which we need to learn here is the Poisson ratio. There is a table here to your right. You will find material, different material, and mu here is giving you the Poisson ratio for steel, copper, bronze, asbestos. The largest number you will find 0.46 for mu. The smallest number you will find it for fiberglass reinforced plastic, which is about 0.22, for example. So what's Poisson ratio? Poisson ratio expresses the strain, the transverse strain divided on longitudinal strain. Longitudinal, you know the longitudinal of the pipe. Transverse is the other side, the perpendicular side over the pipe. So if you divide this transverse strain over longitudinal strain, so dimensionless parameter, this will give you the number of Poisson ratio. This you can find more in this reference down there. What about this psi? This psi here, we know all the letter here. We know the K, the D, the E, Young modulus, bulk modulus, diameter, thickness, density. What about the psi? The psi is a new parameter. You will find it here, C. It's the same. C and psi used synonymously here in the presentation. Again, wave speed calculation. Remember, the wave speed calculation, it's already embedded in your program. It's already, if you look for Excel sheet, you will find many Excel sheets that calculate this for you, but you need to learn how to calculate it, okay? Don't depend on Excel sheet, don't depend on that the program will give you the right answer. You have to calculate this by your hand. It's ranged from 300 meters per second for PVC up to 1400 for steel pipeline. So steel pipeline is the highest one. The PVC or polyethylene is the lower end of the value of the PVC. Depend on fluid properties, pipe material, longitudinal strain. Here, the word longitudinal strain. This is what we need to learn, the different kind of strain. I have another slide which explains this very clearly. What kind of strain here? You have case 1, case 2, case 3 with different strain. In the next slide, I explain it clearly. Case 1, if I have the pipe anchored at the upstream, please assume the upstream, this line here represents the reservoir, and this part represents the valve. So if it is restrained or anchored at upstream end, i.e. at the reservoir only, you will have this expression to calculate the psi. If you have the pipe anchored against axial movement, anchored against axial movement means it's supported here and there, so no way it will move horizontally. You can use this expression. So in number 3, it's exactly similar to 2, except that there is some kind of expansion joint between the pipe element. Remember, the pipe, if I have a 10-kilometer pipe, I will not buy a 10-kilometer one piece. It will be joint 6 meter, 2 meters, 3 meter pipe. It will be connected together through expansion point, joint. So this is the expression here. So I have 3 kinds of expression. This is for the sake of exercises to do. This is the general expression for how to calculate the wave speed. Remember, this must be used for thick wall if it is D over E less than 40. It must be used. If I have a D over E greater than 40, I can also use the same equation here. It will give me more accurate calculation for the support. You can find this in Waters 84, very clearly defined. Again, I will give you a small exercise. If I look to a figure like that, before I read that example, this is supported at the reservoir, this is supported at the valve. Which part? Which case here? Which case represents support at the reservoir and support at the valve? It's case number 2. So case number 2, I have a psi like this. I will put it in the equation here and then calculate that in that exercise. A simple system composed of a reservoir, upstream end, steel pipeline. So if it is steel, I can go directly to 207.7 from the first table. If L is for 4800 carrying water, so water, I know that the density is 1000 kilogram per meter cube, free of air, alhamdulillah, it's free of air and gas, so the value of wave speed will not be affected. And above downstream, the pipe anchored against any axial movement. Remember, case 2 is the most conservative one. So this is the one which can give you the highest number of wave speed. So if it is anchored against any axial movement, I will apply the equation number 2 and then substitute. Please, I encourage every one of you to calculate the psi. I put the answer here is 0.9531, and I put also the number of 1225 meters per second. This is the way we calculate the wave speed. Remember, the maximum number of wave speed is about 1450, 1460, which is the wave supersonic speed in the water, right? So following that, you will find the wave speed through steel. I will have the same exercise here with using chart. If you look to that chart, this is a very, very beautiful chart. Give you this as a wave propagation velocity meter per second. You will have on the horizontal axis here is the inner diameter, divided the wall thickness. Remember, inner diameter. Inner diameter. Don't get the outer diameter. Why I'm saying this? Because polyethylene, high-density polyethylene pipe, if I give you number, the name of the polyethylene is with the outside diameter. So you have to calculate the inner diameter and then divide it by the thickness, divide D over E, and then go to the table to see where is D over E, and then get to the material, with, for example, steel. Let's go back here. For example, if I divided D over E, if some of you have a calculator, D over E, it's a little bit less than 40. So it's exactly similar to here. If I go upward with this vertical line, with the steel, you will find 1225, 1230. This is good enough for a chart to give you the exact number of wave speed. Of course, it will not give you the effect of anchoring. So the anchoring effect, which is this equation, you have to calculate it by your hand. No chart will give you that. If I have another chart, which is a very beautiful chart, different than the one we saw previously, the wave speed, which is C, as I said to you, sometimes I write a C or sometimes an A, meter per second. The vertical axis here is a Young modulus. Different type of material with different value of Young modulus. This will give you the range. This will give you the range of Young modulus. For example, the steel, it will be like 2.07 Newton, let's say 2 Newton per meter square. It's exactly similar to the value which we have find previously in the previous page. If I go D over E and find it exactly about 40 in this exercise, you go up, you will find with E, you will find the value of C. Again, I can use the chart when I don't have a calculator. Nowadays, everyone has a calculator. Even in your mobile, you have a calculator. So please know how to calculate that. But don't ever make a mistake of the wave speed, because it will make a hell of a difference. Again, next, wave speed, wave velocity for varying air content. Remember, this is a very important chart. And if you can notice that the reference in 1965 or other reference by Prisal and Covey, this is the famous two literature which discuss an experimental result with theoretical result with wave speed, getting percentage of air content. Can you imagine if I have a 0.1% volume of gas with respect to the total volume, 0.1, you will have a reduction over 50%. Can you imagine that? A 50% reduction of the wave speed due to the existence of undissolved gas, a bubble. Don't say I have a water and the water has an air, so I have a reduction. No, it is not that way. We are talking about undissolved gas. This is based on experimental things. The impact of transient. Now we learn how to calculate the Joukowski pressure. We know how to calculate the wave speed. Now, what next? Joukowski or Olivier equation, which is the same equation. Both those persons work in a different place, they have the same equation. Estimate the transient pressure rise due to an instantaneous change in the momentum. So delta H is equal to minus A delta V على G. For example, again, if I have A about 1,000 meters per second, in a concrete pipe, for example, if I have a delta V means I have a valve closure, the velocity was 1 meter per second, it becomes 0, a sudden closure. So the delta V here is 0 minus 1, it would be minus 1. Minus 1 multiplied by 1,000 divided by G, assume it is 10, you will have a delta H of 100 meters. Okay? Also be aware of another things will happen. So here we know that there is a delta H increase, and also you need to calculate the thrust force where You remember the momentum equation? When we have a support for the pipe, remember, when you calculate the support of the pipe, take care of that increase of the pressure to get your full support of the pipe. Take care of the oscillation of the wave. Take care of something called resonance. We are not going to study resonance in this course. This means amplified with time, and instead of decaying the result, it will be amplification of the wave, and this will normally happen on reservoir, a lot smaller reservoir. Characteristic time. Now we have to learn something new. What's a characteristic time? We define the characteristic time as a 2L over A. 2L, L is a length, A is a wave speed. If we multiply 2L over A, we call this a system has a characteristic time of 2L over A. Okay? So for example, L, if I have a pipe with a length of 1 kilometer, is a 1,000 meter. 2 multiplied by 1,000 meter divided by wave speed over 1,000, so it will be 2 seconds. So L 1,000 over 1,000 multiplied by 2. So the characteristic time of this is 2 seconds. Again, if I have a characteristic time of 2LA, is the time required for a pulse to travel from far end and then return again to the upstream end. So the traveling start, I'm saying this for the third time or fourth time, the traveling start from the place you initiate the hammer. If I initiate the hammer at the downstream valve, so the hammer will start from the downstream going to the upstream. So, and then go back again to the valve, it will be 2L over A. 1L over A from the valve to the reservoir, another L over A from the reservoir to the valve. So it can take a fraction of a second if it is a short pipe. If the pipe length is a 10 meter, for example, 10 meters. So do you imagine 2 multiplied by 10 meter divided 1,000? Can you imagine how many milliseconds this? It can take 10 seconds, tens of seconds, 1/10 of second, or tens of seconds mean tens يعني 10 بالعربي. In a force main, if I have a 10 kilometer, for example, it can be 2 multiplying by 10,000 divided by 1,000, it will be 20 seconds. It can be minutes if I have kilometers, several kilometers. If I have 100 kilometers, it can take minutes. So the characteristic time depend on the length and the wave speed. What about system response? System response is another thing. Now, don't be confused. The previous one, it's called characteristic time, which is depending on the length of the pipe, the wave speed. You multiply by 2 because it's back and forth. But what about system response to change? This is where we calculate the effect of the parameter which initiate the hammer. For example, if I initiate the valve closure. So the valve closure time of closure with respect to the characteristic time, what will be the ratio between them? What will be, is it larger, smaller, very larger? This is what we are calling the response, system response to change. Compare it to 2L over A, for example, valve movement or pump population. If I say that instantaneous closure, valve closure, or instantaneous pump failure, for example. So 0 time means that the time which I close the valve in a 0 second compared to the 2L over A. Number 2, it can be less than or equal to L over A. We have to distinguish, and I'm going to tell you why. If it is less than or equal to L over A, it means I close the valve in a time less than 2L over A. So the valve closure, go to the reservoir in 1L over A, return from the reservoir in 2L over A. So if my valve closure less than this 2L over A, I will consider this as a rapid. and it required elastic theory. And we're going to solve this with method of characteristic. If it is larger than 2L over A, larger means I close the valve in a time larger than the wave will go and back, and still the valve is closing. So it's larger than 2L over A. We consider this as gradual. So if it is closed in a large time, I close it in 1 hour, 2 hours, 3 hours, it's called slow. At that point, I can use a different theory. I don't have to use a sophisticated theory like elastic one or method of characteristic or many things like that. So in large response or slow response for the system, it's larger than 2L over A, and I can use different theory. In our study, in our course, most of our response will be rapid or gradual. So we're going to use the elastic theory in both of them. Propagation speed, elastic wall. Again, quick example. How long does it take for a pressure? How long does it take for a pressure wave to travel 500 meters after a rapid closure? 1 meter pipe diameter, 1 centimeter wall pipe thickness, steel pipeline. If it is steel pipeline, go to the table directly. E is about 200 gigapascal. And I give you another requirement in this question. I give you if initial flow velocity is 5 meters per second, what would be the increase? So first, it asks you to find out how long it will take to travel the 500 meters. In another word, you have to calculate the wave speed to get that answer. In the second question, if I want the increase in the pressure, you will go directly to the Joukowski equation. Let's see the solution. E is 200, D 1 meter, E 1 centimeter. If you divide diameter over E, put them in the same unit. Don't put 1 over 1. If you put this, it will be a fatal mistake from you. Number 2, if I use bulk modulus, you know the bulk modulus of water is 2.2 10 to the power 9, rho is 1000, and then the gigapascal of steel is 200 gigapascal. You calculate this, it will be 1000. Let's assume 1000 for the sake of simplicity. If I have 5 meters and I have 1000, so L over A, it will take time equal to half a second. So I will travel the 500 meters in half a second. So delta H is minus A delta V over G. Delta V here is 0 minus 5 because I'm completely closed the valve. So the velocity will become 0. So 0 minus 5 is minus 5. Multiplying by 1000 divided by 9.8, it will be 520 meters. The 520 meters here is represent the increase of the pressure. Okay, delta P, which is equal to gamma H or rho G delta H. I can calculate this to be 5.1 megapascal or 740 psi or 52 bar, whatever units you can calculate that. And this exercise, I'm going to leave it to you. This is to show you this rapid closure or slow closure. Flow is 30 liters per second, 1000 meter long, diameter 200 millimeter. And we need to know a 2-speed valve. One time it's closed in 1.5 seconds and the other time closed in 6 seconds. And we need to know what will be the pressure along this. Remember, you need to calculate the velocity first to know how to calculate that. To get the pressure, of course. You need to calculate the velocity to get the pressure because delta H بيساوي A minus A delta V على G. Okay? So calculating this, you will have the answer. I prefer you can calculate this alone so you can know how to do it. And the next slide, I'm going to discuss the stress in the pipeline. What we have learned right now, we learned the pressure. Again, 2 things need to be calculated on the pipe. We need to calculate the pressure stress or we need to calculate the hoop stress, and we need to get the longitudinal stress. Two different calculation for the stresses. But before we do that, the P, which we have to calculate here, we need to calculate the pressure increase first. Delta P from Joukowski. Delta P بيساوي minus أو delta H بيساوي minus A delta V على G. And you can transfer this to delta P. And then you add this to the steady state condition. So P naught is the steady state condition. You add to that the increase due to the water hammer. So total pressure will be the initial pressure before valve closure plus the pressure increase due to water hammer. So once you get that P, this P here will go into that equation. You multiply PV over 2E, it will give you the circumferential hoop stress, which is FC or sigma C. And to do the longitudinal, it will be by G square على 4 على by D E. It will be PD على 4E to give you sigma N. So if I need to calculate the hoop stress or the longitudinal stress, this is the way to calculate it. It is not the P only, it is P represent the static plus the transient. Again, it's another exercise. It's for you to solve. It's a similar. This is here we are ask you to get the FC and FL. In this slide, I want to show you the PVC or high density polyethylene pipe. There is another things I need to take care or to be worried about. If I use a high density polyethylene or if I use a PVC pipe, the hoop stress, for example, this is about 1,000, this is 6,000 PSI. This is cycle for failures. This is the number of cycle of failure. What do you mean cycle of failure? Cycle of failure, this pipe will be experience hammer action on and on and on every day 10 times, every day 1 time, every day it will repeat it, hammer action. It means they are stressing the pipe and then back, stressing the pipe and then back to normal, stressing the pipe and then back to normal. This is called pressure rating over time. Unfortunately, the PVC and high density polyethylene, it will be reduced dramatically with time. This number is a number of cycle. Sometimes you will find a graph give you the number of hours before it fails. But this is the importance of this figure is to show to you that along the time or with time, when you do your analysis or when you use high density polyethylene or PVC pipe, you have to take into your account that with time that the hoop stress will be less and this pipe will be experience a lower pressure rating in your design. So this is things that need to be taken care in future when you are after graduation, when you are going to use high density polyethylene. It is not, I'm not going to ask you during our course about this. Now, we have to distinguish. If you can notice that I'm getting you step by step of the design, step by step to get the value of the hammer during our design. First, we experience the Joukowski pressure. Second, we get into the stress by adding the steady state condition up to the delta P to calculate the pressure and getting the stress. Number two here, we need to distinguish between occasional and recurring pressure. What do you mean occasional? Occasional بالعربي يعني تحصل مرة يعني كل فترات طويلة. Occasional. Recurring, at least إذا حصلت لك مرة every day, once every day, I can call this as a recurring or repetitive pressure. So you have to distinguish between the short term and the repetitive term. Short term is peak pressure surge caused by event outside the normal operation. So normal operation means the pipe is normally at 8 bar. It's working at 8 bar. Suddenly it becomes 10 due to the hammer. It's increased 2 bar due to. So this is called occasional. Recurring, if it is repetitive, if I use a pipe 8 bar and then During the day, it becomes 10 and then return 8 again. And it becomes 10, return 8 again. So this is called repetitive pressure surge. طيب يبقى احنا عرفنا الفرق بين الاثنين. In considering potential of short-term impact, again, لو تاخد بالك, if you notice, I'm getting you step by step. Which part I have to take care of? Which part I have to be worried about? Which part I have to calculate and look at it when I have my diagram? In considering short-term, the impact of surge here, the following factors need to be addressed. Upsurge, it's a pressure increase over a pressurized pipeline leading to a pipe damage or rupture, or damage the system component. So I need to look to the value which make that pipe ruptures. What's the maximum pressure? What's the maximum pressure during the upsurge which give me the failure? During the downsurge, I have another things I have to look about. Is the downsurge is a pipe can sustain, can succeed during the lower pressure? We know that we did not reach the vapor. You and me understand we are not talking about vapor here, but I'm talking about upsurge and downsurge. The maximum pressure, the lower pressure. So we need to look at that. Identification of peak surge. Again, this is a step-by-step. The maximum events over the course of the pipeline design. If I'm designing a water hammer, if I'm doing a water hammer report, and I'm designing and to see the maximum events, as a designer, I have to look to the maximum event that will happen during the lifetime. You can ask me lifetime, or I'm going to look for the lifetime of the pipeline. Yes, you're going to simulate that. You can imitate that. You can design the lifetime of this pipe, and then look for everything that will happen to that. Everything can possibly happen to that pipe. So the maximum event over the course of the pipe design, this is called the lifetime that need to be considered for surge resistance for design purpose. So we are looking for the peak. Here, as a hammer designer, we are looking for the peak. Okay. So at the start, I told you to give me the history, maximum, minimum, normal history. And here, I'm asking you to calculate what will be the maximum peak surge so I can design my protection. So maximum design velocity or maximum anticipated water flow velocity. So I need to use that one to get the maximum peak. The worst case anticipated event, it's emergency things. If it is a trip of a pump, it's gone out of electricity, or someone shut it unexpectedly. So this is the worst anticipated scenario that you have to look at. So this is the way we explained identification of peak surge. This is the way I look at it. So if I have any action like valve closure, I have a wave like this, and there is a peak, and then down surge here, and then another peak, then down surge, and so on. So where do you look for the maximum? Maximum velocity will give you the maximum pressure here, P maximum and P minimum. So for all this diagram, which represent to you the pressure history, this is what you have to show to me. When you learn hammer and when you understand the hammer analysis, you have to show me the pressure history. If you show me the pressure history, you can calculate easily the maximum pressure. You can calculate easily the minimum pressure. We'll learn later what to do with this. Okay, and later means next slide. So we learn what to do with the maximum pressure, what to do with the minimum pressure, how long it will take to die in. This is a good information to learn. We know that it's dying due to the steady state friction, or we're going to reach the steady state. All this is excellent. But if I am a designer, I'm looking for the worst thing. Unfortunately, as an engineer, you look for the worst thing to protect. You look for the maximum you look for the minimum. Okay? Again, what's the maximum allowable pressure? So this is the second logical question. If you know how to calculate the maximum pressure, if you know how to calculate the peak, the maximum peak surge, and then you calculate the maximum and the minimum, what will be the maximum allowable pressure here? The pipeline shall have pressure class rating. Yes, we all know what's a class rating. For example, if I say I have a pipeline of 10 bar class rating, it means this is a working pressure. Okay, so the pipeline shall have pressure class rating greater than the static working pressure plus in addition to the surge. So when you choose a class rating, you need to choose a working pressure plus surge pressure that will be covered by the class rating. For example, if I have my working pressure is 8 bar, and I know that with the increase of pressure, it's another 2 bar, so it's 10, so I can use 10. So if it is working pressure 9, and then I have water hammer 2 bar, so it will be 11. I cannot use 10 bar. Do you understand that? So the maximum allowable pressure means that the class rating that you're going to choose for selecting the pipe must be greater than the static or the working pressure plus the surge pressure. Here, I'm going to close my lecture here with a very nice slide. This slide here is from reference from a book called Water Supply System Analysis, Selected Topics. And this paper, which I got that graph, is from I'm going to tell you the name, but this is the first paper on this book. Okay, this is called, it's calculating the maximum allowable incidental pressure, MAIP. It's a maximum allowable incidental pressure factor. It's two things over each other. We will get the allowable maximum pressure operating, PMA, divided by allowable operating pressure, PFA. For example, here, this number with the first number here, PMA, this is everything. It's static plus transient. If I add those two together, I will give you, it will give me the allowable maximum pressure. If I divide this over the operating pressure, if it is 1, means I am choosing a pipe, a class rating pipe, which is equal to the class rating itself, equal to both the static and the transient. So if I divided those two parameters over each other, it will give me the same number over each other. So it will be 1. If I have, and this is the code. The code means, this is a German using that. They use that. They will not allow for a class rating pipe that will exceed both the static and the transient. So both of them, if you divide them together, it will be 1. On the ASME B31, if I can use PMA larger than the allowable pressure by 10%, for example, if I have both static and transient, both of them equal to 11 bar, and I divide them by the class rating, which is 10 bar, 11 divided 10, it will be what? It will be 1.1. So I allow, as a designer, based on this code, I allow a 10% increase over the working pressure or the class rating of my pipe. On the NEN European standard here, it will allow for 15%. On the BS, the British standard, allow for 20%. On the Italian, they allow a range between 25% to 50%. What I'm going to do, I'm going to use 1. We're going to use the first one. I will not say to you why, but I'm going to use 1. I will not allow for maximum pressure or class rating of the pipe to exceed more than the same class rating, static plus transient, If I divide it over the cross rating, which is the same, it will be 1. So this is the way we are gonna use our design.